Hi, everybody. Welcome to VSAONLINE. Today, I'm very glad to host my colleagues from Moscow, IERI Research Institute, um, Alexey Kovalev and Alexandr Korchemnyi. They will give a talk about symbolic disentanglement. So without any further delay, so the floor is yours, guys. Please.
I'm sorry, I'm just call off from the conference. So one moment. Okay. Yes, now I'm ready. Okay, I start sharing my screen and then. Okay. Okay. Hello,
Yes.
everyone, and Evgeny, thank you for introduction. I lost your introduction actually, but I hope it was very nice and you give some brief idea about our talk. And today I'm pleased to talk about work together with Alexandr Korchemnyi. It work about symbolic disentanglement representations for images, and actually it was done under the supervision of Alexander Panov. And agenda for today will start from some introduction, and I give the context of our approach. Then Alexander continues the main explanation of task and how we approach this task with some kind of technical ideas. Then we talk about disentanglement metrics and why do we have introduce new metrics that's suitable for representations we work with. And then we'll show our main results and the datasets which we work on. Actually, it's synthetic datasets, but on the next section, we also show how our approach could be extended to real-life images and some kind of preliminary results that we obtain on these images. And of course, we'll complete our work at the end. Okay, let's start from introduction. And I just want to give some brief context about disentanglement representations. And usually when we work with some kind of unstructured data, it's images in our case, but it could be anything. It could be audio signal, could be text, video, other unstructured data as well. We want to learn some kind of representation of this data that could be used in downstream tasks. And there are actually different ways how we could learn these representations. And one of them is what's quoted on this slide. That the most robust approach to feature learning is to disentangle as many factors as possible, discarding as little information about the data as in practical. And the idea here that actually our observable data is generated by some process that maps factor variations or generative factors into real life. And we want to find kind of mapping from this observable data to these factor variations and get the representations that has some particular feature, or maybe some particular vector that corresponds to one of these factors. And it could be seen as kind of working with tabular data, then we usually do have these representations in terms of factor of variations. Yeah, we could represent this scene as an object inside some room. There could be object size, object shape, color, void color, for color, and so on. And we can just write it down like in a column, in a row. But in a structured data, we don't have these representations, but we want to learn it. And the problem, how we could learn it. And actually, before learning it, it's really the question, do we need these representations? Because in some of downstream tasks, we really don't care about disentanglement, and other representations would work well. But there's some particular cases or applications. I don't list every application here, but some of them, these representations are useful. One of them is explainability. So if we could separate our data into these features that correspond to some factor variations. So changing this kind of one of this factor, we could see or could predict how our model will behave in the future, or how our answer will be changed. So this gives us the good understanding of the model, and then actually learned representations we use in our task. Another application, it's particularly relative to our approach, is controllable generation of images or some objects with desired properties. So we not want just to generate some like sphere, but we want this sphere will be some particular color, some particular shape, or maybe some particular material. And we know in terms, if you have this diagonal representations, we know which feature or which dimension you have to tackle to get this particular result. And another application is causal reasoning. It's hardly related to explainability, so it could not just explain the behavior of the model, some particular data, but to construct a chain of reasoning and see how one data relates to another data. And another example is data compression. So if you talk about images, let's say this data, this observable data on the left is like a 64 by 64 image with 3 channels, but we could represent it in terms of 6 factor variations, like object size, shape, color, wall color, floor color, and angle, viewing angle. So this helps us to reduce the amount of memory this data consume actually. But the problem with learning them, that it was proved that if you try to learn these dark representations in unsupervised manner, it's actually impossible without some additional inductive biases. What we consider in terms of learning approaches or in terms of data sets we use to learn these representations. And in our work, we use some of them, restriction. So first of all, we use very simple reconstruction laws, and it's actually just mean squared error. What we compare the initial image and generated image. And of course, this signal is not enough to produce good inductive representations. So then we combine weakly supervised learning with specially constructed data sets, which we call like pairy data. It helps us to understand which particular factor is changed in this particular object. But this is from the view of like traditional like neural networks or traditional machine learning. But the hyperdimensional computing gives us the power of what we call disentanglement by construction, because we can use this principle to represent an object as a superposition of its attribute value pairs in a way that we could combine it in one object, and then using operations like binding or unbinding, we could deconstruct it into its initial features, initial attribute values pairs, and also we could obtain the values from this values attribute pairs. So this is actually gives us this disentanglement by construction if you talk just about hyperdimensional computing. But another challenge here that traditional like neural networks use localist representations, and they very good in working with unstructured data, and we could very simple to use encoder-decoder architecture to encode some particular image into Latin space, and then to decode it into the same or like similar image. But these networks will use localist representations. On the other hand, hyperdimensional computing that gives us this power of like disentanglement by constructions uses distributed representations. And it's very tricky how we could actually ground it to real data or to unstructured data. There are several cases, there are several other works who do it in different manner. But in our particular case, we use, like to be a small spoiler, we use a attention mechanism that helps us to bridge this gap between local list representations and distributed representations, and it helps us to exploit the power of neural networks, but helps us to ground our representations on unstructured data, and then use, on the other hand, power of hyperdimensional computing. It helps us to construct these disentangled representations and do it in very explainable and clear way. And on this part, I will stop the introduction and give the floor to Alexander. So Alexander, you can start sharing your screen. And you can continue.
Hello, everyone. So I think you can see my screen.
Yeah.
So let's start. Now we talk about our approach, and let's briefly discuss why we're doing all this. And there is 3 types of tasks we can accomplish. We aim to decompose the original object in a set of generative factors. We can generate a new image, a new object from a predefined set of generative factors, and we want to manageably change the current scene or object, and we can manage generative factors with using a symbolic approach while working with vectors in neural networks. And in this work, we want to combine these approaches. So let's. So on the screen, you can see a simple object. It's a cube, and it has a set of characteristics listed on the right: shape, color, and so on. And looking at the image, we can see only the object, but in reality, there is many additional things: background, light, perspective, angle, camera distortion. Moreover, in theory, you can add almost infinitely many characteristics such as weather, time of year, which at this moment do not relate to this image, but it would be reasonable to take a limited set of generative factors in the current in the current image. Ultimately, the main assumption that we immediately limit the set of generative factors under discussion. Once we have established the set of generative factors to be considered, we can start extracting them from the image. Usually, it's a simple classifier that takes an image as an input and output a latent image vector, which is then classified to the necessary classes, or regression is used on real numbers, like a position or rotation. It's simply convolutional neural networks or a visual transformer. So that can be used as encoder. The second task is to generate a new image from an already existing set of features. It's assumed that the new object, in addition to the clearly fixed selected features, has others with the most probable value, like the background color. So in this case, we can use some type of decoder. It's usually a convolutional model, GAN, or a diffusion model. And typically, the task of decoding image from the set of generative parameters is much more complex and requires a fairly large data set. So let's talk about controllable scene generation or controllable scene editing. So in this task, it's necessary first to decompose the scene to the set of generative factors and then change some of them and generate a new image. It's usually in such cases, some of characteristics don't change and remain the same. On this slide, it's important that the most characteristics of the objects in the scene remain the same. And it's even to the main generative factors may change, the background and other surroundings remain the same. The more characteristic change, the more the task turns into ordinary generation of a new image, which we considered earlier. And in our work, controllable scene generation plays an important part. And for the idea presented in our work, it's crucial that the most parameters of the objects in the scene are the same. So regarding the architecture that is usually used to simultaneously train the process of decomposing an object into a set of features and the process of generation a new image, a new object from the existing set of features, encoder-decoder architecture is most often used, which learns end-to-end using MSE laws. So now we talk about main training idea, and we consider exchange of a single generative factor, and we observe the main block of our architecture, and then we try to follow step by step to obtain a VSA representation of an object. So let's start from our architecture. It's about exchange of a single generative factors. So let's consider the image. Imagine you have two scene images that differ only by one value on one feature. In this case, a slide shows two images from the Clever dataset. There are two cylinders with a list of generative factors they consist of, like this. The shape is a cylinder. The color is red or purple. Size is large. Material metallic, and they have the same x and y coordinates. It turns out these two objects differ only in color. In this case, if we pass both images through the encoder and get their latent representations, then their latent representations will differ only by one feature. If we can obtain a latent representation that is also divided into individual properties somehow, then in such case, all properties except the one that differs should match. At least it will be desirable then to match. So if all properties except one match, then in this case we can exchange the different property and reconstruct the original objects crosswise. So for readability only we reconstructed the purple cylinder, but you can also add a red cylinder with color property and reconstruct it too. So you can see end-to-end training architecture that allows learn individual object representation or object properties in special places. So like color in the second position. So let's take a closer look. We have a training dataset where each training example contains two images and with generative factors, the size, the number of generative factors is n. So each image may be considered as a set of generative factors, and each of these images can be donor for the other. And we have a feature exchange vector with 1 or 0 values. That is means the value is the same or or it isn't the same. So we can obtain a vector symbolic representation of the original object. So we can we try to formulate what is consist of. The final object vector will have the same dimensionality as its individual generative factors. And the final representation is the sum of individual values, so generative factors after a binding function on placeholders. So we can bind value to the placeholder. It's names of generative factors themselves. And this is necessary for subsequent unbinding if need to extract the obtained value from the overall vector for altering the scan or editing the scan latent vector. We can obtain the final vector consisting of individual coordinates, like the red cylinder of this. So we refer to top image. Its shape of a cylinder bind to the value of cylinder, and color bind to red, like size and etc. Then we obtain then we can find the vector in the item memory. We need to create this item memory first, and we at the start we can use an implementation of HD vectors that consists of real values sampled from the normal distribution, and we can use a cosine distance as a similarity for function between vectors, and we can sample k vectors corresponding to the number of possible values of generative factors, generative factor, and we use dimensionality like 124. So for our case, there is 6 generative factors in the dataset for the image. So we create 6 separate item memories for each generative factors, each with its own number of vectors suited for the specific generative factors. We experimented with a scenario where the number of vectors in each memory was the same. It was a large value, which lead to a similar reconstruction result, but significantly worse disentanglement. So let's do step by step obtaining a VSA representation of an object, and in this case, it's simple simple description. So we get each vector, and then we bind them to the placeholder generative factor, and after that we are sum all of them to obtain an object representation. So regarding obtaining a vector symbolic representation from the original object, the process is slightly different. Initially, we obtain a hidden representation of the object, like this red vector. After we pass it to encoder, pass image to encoder. Then we do projection of generative factors, and we divide this vector into several vectors, each corresponding to this property, to generative factors, like n vectors. And the feature vector may differ from the object vector dimensional. But in our experiments, it's both the object vector and the feature vector, as well the memory vectors, have a dimensionality of 124. So after we obtain vectors responsible for individual object features, and like this projection, we do the main attention mechanism to get our vectors from item memory. So we need we can obtain these vectors, but they they can be used to object reconstruction and so forth, but they can they lack the necessary properties. They're not from a normal distribution. So even one non-random coordinate in this vector is enough to understand the feature value for decoder, and it's not that we are looking for, because that set is fairly simple and it's possible. So we want our object representation to be alterable using vector symbolic operations. It's not possible if only one coordinate are doing all this work. So we aim to match some vector in item memory with the object feature vector. So we are choosing the most similar one, like this, like obtaining coefficient and multiplying them in each vector in item memory, and we're getting a weighted sum. But like if we're using the soft maximum function, usually one coordinate is very big and other are very small. So it's not an argmax function that is not differentiable, but it's softmax. So we are getting our gradients through the further learning process. So then we, after we obtain our feature vector from our item memory, we are binding them to the placeholders also, like we are done yet, and then we sum them to obtain our object representation. We're finally getting object vector. So then we can decode the final, after we're getting our object vector, we can decode them to initial image, calculate MSE loss, and run iteratively training process. So we are using, you can see a model architecture like encoder and decoder parameters. It's not a complex architecture, allowing more focus on the attention mechanism of object vector acquisition. So this encoder and decoder architecture are also used on for other models to compare, and in slot attention model we're using in later. And there is attention layers. So we're using two attention layers, K and Q, and we're not using projection for item memory vectors. So now let's talk about disentanglement metrics. And there is a problem. So we propose two metrics, and we cannot use conventional metrics that is designed for latent vectors in other work, whereas each coordinate corresponds to one feature, because in our case, an entire vector, not a single coordinate, represents one feature. So we introduce two metrics. It's disentanglement modularity metric and disentanglement compactness metric, called as the same for usual disentanglement metric, but there is a difference. These metrics work at level of comparing reconstructed representations, not a latent representation. we have an original object vector, and then we try to modify an original object vector with only one feature. Then we decode them, decode the latent vector and into image, and classify all generative feature values using pre-trained image classifier. Then we do the same for modified object, getting modified image, then do the classify also, and then we compare them and getting hopefully we're getting only one difference. So we're comparing is one value is not equal to another, we put 1. If it's equal, we put 0. Correspondingly, 1 means so we can use a different classifier. We do this approach for checking each property, each generative factors separately. So, for example, we are doing for only the second feature. Then we getting for all test image randomly selected from our test dataset, and sum all these values like row-wise, and getting some vector that we then we apply a softmax function on this vector and calculate calculate entropy. So if only one vector was changed for all for only one vector was changed, we're getting low disentanglement modularity metric, because entropy is low when it's only one value is high. And if we modify only one values and classifiers can get several values, then it's a bad situation and we get high entropy. It's the first type was disentanglement modularity metric, and the second type is disentanglement compactness metric. It's like a column-wise sum. So we sum all the values into column-wise, and we're expecting getting only a value of 1. So if this value equals to 1, we're getting we're subtracting 1, and we getting model value. So if only one feature was exchanged, we're getting 0 overall, and it's growing with a growing error. So there is a mathematical equation to explain this approach, where the C is one unit of Latin representation. We're getting we get the entropy function in the classifier, and we have a vector set of all values. Okay, so let's continue. So now we discuss our data sets and results that we get. The first data set is disparate data set. It consists of 100,000 of pairs of images, mainly constructed randomly selected, where also generate 30k pairs to test split. Ground generative factors for this dataset was only 5. Its shape, scale, orientation, position X, position Y. For checking the compositional generalization, we're removing from the train set all images where a shape is square and position X was to the right. And we used IOU metric to get to understand how good is reconstruction. So there is an example for reconstruction in our dataset. 1 second. It's crashed PowerPoint. I'll try to restart. Can you see? Oh, again, I hope you can see.
It appears in a separate window somehow.
So I need to restart, I think. Alexey, can you continue while I'm restarting?
Yes, let me start to sharing the screen. I think it will be simpler.
Yeah, it will be faster.
Okay.
Sorry.
Just 1 moment. Okay. So do you see it on the full screen?
Yes.
Okay, Alexander, you can continue.
This in first column, it's an image. It's a first image, blue color. It's a donor image, and they are different in this image, not only by one feature, but the several features. We can exchange several features at once, also, and we still can get cross reconstruction while we're exchanging several functions, several generative factors. So you can see a reconstructed image, like it's a very simple data set, and model can capture all generative factors. Also, you can see and squares on the right that is shows that compositional generalization it's also work. Next slide, please. On this image, you can see a clever pair dataset. It's was generated by us from the code from the official code of the clever dataset. That it consists of 2 images that differ only by one feature. We test several exchanges at once, but it not on this slide. So it's a more complex dataset, and we used less images for this dataset. Only 10,000 pairs and 1,000 for test pairs. It have 6 generative factors, and it has a different method to check for compositional generalization. In train, we have special combinations of colors and objects, and in validation split or test split, we have all combinations of colors and objects. And we use a fit metric to calculate the similarity to the original Clever dataset. Lower is better. So you can see a reconstruction results on these images, like the one before, and we can do further. Next slide, please. This slide shows the metric we obtain on these two datasets. Like most results, we can calculate, we can compare our approach mostly on the Clever one period, because there is a problem with factor VA and with classifier metrics in Dispride's dataset also. So we calculate. So you can see, and let's discuss disentanglement modularity metric. It's the best in the factor VA dataset, but we like the factor VA has 10 coordinates in latent representation, and it has better disentanglement compactness metric. And you can see beta VA has like 6 latent like vector of 6 coordinates, and it has better disentanglement compactness metric compared to factor VA, and we have the best result in this metric for our approach. Next, we tried to calculate intersection over union in Dispride dataset for different size of latent representation. So you can see the results, and the bigger size is better, like you can see. So let's go next slide. In this slide, we can show you can see how we tried to reconstruct an entire object from only one latent factor, and it's not reconstructable, but so it's good that objects are represented by the sum of latent factors. So it shows that we achieve like truly disentanglement in this image. But you can see a nice rows or columns in the right. It's like a reconstruction of X or Y positions. And also you can see that several images are entirely black. It doesn't reconstruct it somehow. So we are not using all item memory vectors. So we're using only almost a half of them, but they are differ in X and Y positions. We are not using too low amount of them. And where we are using a bigger latent size, bigger item memory size for each generative factor, where not we cannot see this like completely reconstructed the y position. So it was more more splitted for all vectors. So let's go next. This is also the same approach for the Clever one paired dataset, and you can see an XY positions in this dataset was like angled. So X it's from the right bottom to the left top, and Y it was from left bottom to the right top. So let's go next. And we also checked our approach into more realistically data. We tried to do the scene editing approach with our training setup. And no, let's start. Like, we generate the Clever 5 dataset that is consist of 1 to 5 objects. They're differed only one in only one object. So in the top row you can see different color. In the middle row you can see a different Y position, and in the bottom you can see different size. So let's start discuss about next. We used a slot attention mechanism to decompose the initial scene into different objects. Like the first row, you can see slot 1, slot 2, etc. We can obtain masks to cut any objects using a slot attention approach. We use 6 slots. That is one more than the maximum amount of objects, and 1 slot is for background. We used 3 times attention mechanism, like in the original paper, and so we can obtain the separate objects from the initial scene using the attention mechanism. Then we are choosing one object that we tried to change by the similarity of function. Then we try to exchange. We have an object in our dataset that is differ only one generative factor from the selected one. We do the feature exchange mechanism. Then we project with slot MLP module to the initial slot attention slot, and then we reconstruct scene with decoder, combining it with original reconstruction scene, and also we do the donor reconstruction with the main object features. So we're combining these losses together. So this is a three MSE losses summed as a loss function, and this is end-to-end mechanism to train, and it's allow us to edit the scene if it's is symbolic vector symbolic representation of an object. We can use vector symbolic operations to edit the scene. So go next slide. So you can see results where we try to edit the scene. So the first row, so the first column is a ground truth scene. The yellow color, it's reconstructed. It's ground truth. It's no, sorry, sorry, it's not a ground truth. It's just a first row in the last picture, like a reconstructed scene, and we edited it. And to the right, you can see ground truth edited how it should be. We're obtaining a fit metric like 67. It's fairly low compared to other disentanglement frameworks. So go to the next slide, please. We test our approach on the celibate dataset, where we so in original celibate dataset is consists of many images of celibs, and it has around 40 binary features. We selected 7 features from this dataset and combine them in generative factors and create 10K pairs while using the same architecture like for the Clever dataset, because images has the same resolution like the other, like in the other disentanglement frameworks. So you can see the results of reconstruction cross exchanged images, and you can see it's usually understand like the hair color in the second row right. So I'll go to the next slide, please. So it's a conclusion. Let's go next. So we introduced a new architecture to which allows to learn symbolic disentanglement representations. We utilize a structure, and this architecture utilized the structured representation in Latland space, and we are using hyperdimensional computing principles that allows us to obtain symbolic representations and allows us to edit the stand by constructing. We're using distributed representations, which enables us to manipulate the number properties. And we integrate the slot attention architecture which allows us to identify individual objects and manipulate the stand. And we present new metrics to evaluate models with a different latent representation structure. So this is all. Thank you for your attention.
Thank you. Thank you, Alexander. Thank you for the great talk. So let's see if we have questions in the audience. So I see one comment rather in the chat from Adam. Can you say what you meant, or shall
Sure.
I read it loud? Yeah.
Hi, folks. So thanks for the presentation. My comment was about well, a field called probabilistic programming, where you start from having a generator. So these images that you've shown, right? We have some simulator from them, and in some particular cases, this simulator is differentiable, and the output image does depends directly on the parameters. These you call them generative factors, right? And you can optimize the image just using normal gradient descent to fit the parameters and vice versa. So this is an area where you may want to look into. It's not an alternative to using an encoder and decoder as much as it is a different way of doing this kind of modeling in an addition to such setups. If I recall correctly, then you can take your disentangled you would be able to take your disentangled representation, put it in there, and investigate like what the influences of each of these factors on the image, as you've shown, but in a probabilistic sound manner.
Oh, thank you for these references. I think we'll have a close look at this approach. It sounds very interesting and promising. Thank you a lot.
Welcome.
Thank you. Thank you, Adam. More questions? Let's see. I have maybe a technical question about the way how you do the projection. So on one of the slides when you show the architecture, so you have this projection where you split the latent representation into several ones. So do you do it like by several projection matrices?
So where like attention mechanism is like mechanism in transformers, except we have yes, except we have no projection matrices for item memory vectors, but initially we have, so imagine we have 6 generative factors. So we have an object representation like dimension 1024, and then we project it to 6 vectors of dimension 124. Then we have another projection like k-value matrices, k and query matrices.
Okay, I got it. And
then, so technically, this GIF projection is just MLP. So
okay, yeah, I see.
Term.
Yeah, all right. Now I get it. Then maybe one question. So as I understand, so you generate this vectors for values of different features randomly, so they're orthogonal, right? So basically there is no similarity between blue and red and such. Question is, if you tried generating this vector with some similarity in between them.
Yes, we also tried to generate the position vectors, like the all real vectors, using ordering. So we use in real vectors, we're using some power to some natural values of power. So we use 1, but if we use lower value, the vector were more similar, and it's not worked well.
It didn't.
So like it works after 0.2 and more. Like if we do less similarity, it's we do less power, it get more similar, and it's not work well.
And actually, in our current architecture, the selectors are fixed and they're not learned during the training. And we also experiment with unfreezing them and try to learn them as well. And this worked much worse than now. So the idea here that we sampled it at the beginning, at the initialization of architecture, fix them, and this helps us to preserve this property of the distributed representations. So we don't change any dimension of these vectors.
Yes, thank you. So let me see. Do we have more questions in the audience? Maybe it's getting too late in Europe. Well, obviously it's getting too late in Moscow. Well, if there are no more questions, so then let's finish this webinar. So once again, thank you very much, Alexander, for
thank you for your attention.
Yeah, thank you for giving great talk. So and thank you all for joining us. So I see you in 2 weeks from now.
Thank you.
Thank you. Bye-bye.
Thank you. Bye.
Thank you. Bye-bye.